Hello friends, we are going to learn another concept called beams. In this concept, the major topics are determination of stresses and the determination of deflections. In the determination of stresses, we need to understand what are all the stresses that are induced in a beam due to the effect of external forces. So there are two types of stresses that are acting in a beam due to the external forces. One is the bending stress, the second one is the shear stress. So to determine the bending stress and shear stress, we have the formulas. We are going to derive the formulas. So I divide this beam concept into four parts. Firstly, we are going to determine the shear force and bending moment at different location of a beam. Secondly, we are going to determine the bending stress. So first, we will derive the formula and then using the bending moment acting on a beam, we are going to determine the bending stress. Third, we are going to derive the shear stress formula and then we are going to determine for various beams. Fourthly, we are going to determine the deflection that has occurred in a beam. So first, let us go on and discuss the shear force and bending moment acting on a given beam in any part of the beam, and particularly the maximum bending moment and the maximum shear force. These quantities are very much important to be used in the stress formulas to determine the corresponding stresses. Let us go on and discuss shear force and bending moment now. When you watch this series of videos on beams, you see the title below. You see first the title, beams. Then what heading we are discussing, shear force and bending moment. Then the first video will be on introduction. So within the bracket you will see video 1, video 2, video 3. So to follow the beams discussion, you can go and see video 1, video 2, video 3 to understand these concepts in a sequence. Now let us discuss shear force and bending moment in beams. First, let us discuss the types of beam, then the applications, types of load, the definitions of shear force and bending moment, then the relation between load, shear and bending moment in this video. And the subsequent videos we will discuss the problems in different beams in order to understand how to determine shear force and bending moment in beams. There are different types of beams. Beams doesn't mean the structural beam alone. It's a concept. Various practical applications are reduced to one of these cases shown here, out of which the three beams shown here are statically determinate beams. We know what is statically determinate beams. The number of unknowns are equal to the number of equilibrium equations. So in this course, we will discuss only statically determinate beams. Now, practical applications. A shaft supported between bearings or the examples of simply supported beam, and it is also a representation diagram. So practically, shafts are subjected to bending moment and twisting moment. The shafts are designed based on the bending moment and twisting moment that are acting. So bending moment is coming under this beam concept. And various loads are acting on this beam. And if you see this crankshaft, it is also assumed to be simply supported beam. When you design the crankshaft, you will understand it. And cantilever beam, the leaf spring design is based on the assumption that it is behaving like a cantilever beam. It is supported here and load is acting here. So, and the total load will be acting here also. So, based on the assumption of cantilever beam, the leaf springs are designed. And you see, various loads are acting even beyond the bearing. So, it is now overhanging. So, here the belt drives or gear drives that are used to transmit or for transmission, then it is behaving like a overhanging beam. And many more applications are there which can be reduced to the concept of beam. Any one of the beams, cantilever beam, simply supported beam. Overhanging beam is a special case of simply supported beam with overhanging loads. Now let us understand what are the different types of loads. In our earlier course, engineering mechanics, we would have already learned about this. I'll quickly recollect the external forces, the different types of external forces. So, uh, first one is concentrated load or force or point load. So, if this is a cantilever beam, one end is fixed, the other end there may be one load at the free end, another load. These are point load or concentrated load. Second one is uniformly distributed load or distributed load. So if you take a simply supported beam, one end is hinged, other end is roller supported. So there are three reactions in these supports. So x direction, y direction, and here only the y direction. So three unknowns are there. We will be able to find out these unknowns. And distributed loads, it can be uniformly distributed like this or linearly distributed like this. Even parabolic way the external force may act. It is expressed Newton per unit length meter. Here also it is W Newton per meter. One end it is 0, other end it is having W Newton per meter, and uniformly it is varying. So uniformly distributed load or uniform linearly varying load. So these are the three types of loads we are going to discuss in this course. That doesn't mean we cannot use other loads also. Some loads it may act very parabolically, so it may vary like this. At this curve will have some equation also. So want of time, we will not be discussing this in this course. The concentrated load, uniformly distributed load, and uniformly linearly varying load. So these are the three forces, external forces we are going to concentrate. So when there is a uniformly distributed load that is acting, it can be represented like this, or in other diagrams you could see like this. The force are distributed, uniform. You could see this also. Now, as such, we cannot use the load. So, in our engineering mechanics class, how to change this load into a point load, we would have already understood. For that, we have to consider this as a rectangle. To consider as rectangle. So the area of the rectangle, okay, you take this as W and this as L, the length over which it is distributed. So the area is the shear force or the concentrated load. Area will be W into L, W into L. So that is the force that is acting. So it is expressed, omega W load is expressed Newton per meter and L is in meter. So we are getting Newton. W into L is Newton. So where it will be acting? You have centroid. You have centroid for this area. So this external force will be acting, passing through the CG. So W into L, and it is acting from this end, it is L by 2. From this end, it is L by 2. So exactly half. So this you need to understand very clearly. Similarly, a linearly varying load, how it could be done? So it is a triangle. The same way, it is the triangle. So CG is going to be here. From this apex, it is two-third of the length. If this is the length, this is the length. From this end, it will be L by 3. So this already we know. Now how to change this or convert this distributed load into a point load? So you have to find out the area. So area is, so let us say this is W Newton per meter or per span. Area is half W into L. So half W into L is the force, and that force is acting passing through the centroid. So This is the force that is acting. The force is WL by 2. So very, very important. People make mistake in this. So please understand it very carefully. How a distributed load can be changed into a point load. After changing it into point load, we'll be able to very easily calculate the shear force and the bending moment. Now, let us understand what is shear force and what is bending moment, the definition. Okay, any beam. See, the given beam is a simply supported beam. It is subjected with 2 point loads, P1, P2, and there's a uniformly distributed load. So uniformly distributed load, you can call it as UDL. Uh, Uniformly varying load, you can use UVL. Linearly varying load, you can call it UVL, right? So UDL, WUDL load and 2 point loads are acting. How to find out or how to define shear force? Shear force can be determined or obtained in any point on the beam throughout the length. And any point you pass a section, generally we call it cutting section. What happens? It cuts into two halves, not equal halves, two two segments. Okay, so if you pass a cutting plane through that particular point and separate the beam into two, okay, you have a left side equilibrium and right side equilibrium. You consider any one side, either right side or left side, sum all the forces that are acting to that particular side, and that will be the internal force or the shear force at this particular section C. In this case, if you consider the left hand side, you have the reaction RA, you have P1 and W. Now sum all these three loads, and that will be this V, shear force at C, at the point C or at the section C. This UDL will be converted into a point load, then you can find out. So if you know the length and W into that particular length will be the point load, and which will be acting at the mid of this. So you sum all the left hand side forces, external forces, the reaction forces, and that is the shear force at this section, at any given section. Particularly here we are concentrating at C. Or it is or, okay, or you consider only right hand side, and there are two forces. One is the reaction force RB, other is another point load P2. You sum these two forces, so the algebraic sum of all the forces either at the right side or at the left side is the shear force. That is what we are seeing here. So then bending moment, it is algebraic sum of all the moments of all the forces acting to the right or left of the section. Here we have three forces. These three will produce moment about this point C. So those moments you have to add in order to obtain the moment at this section. Similarly, you can have in this section, in this section, in this section, in this section, any point on the beam, you will be able to obtain shear force and bending moment. I hope you would have understood the definition. You pass a section, consider either right side or left side, sum all the forces, then that is the shear force at that particular section. If you sum all the moments that are developed by those forces, either right side or left side of the section, then that is the bending moment at that particular section. Now, some sign conventions we follow in order to easily obtain shear force and bending moment. Different book follows different sign convention. We are following a positive sign convention, so opposite will be the negative. So any section, this is the given section, left hand side upward forces are considered to be positive for shear force. Right hand side forces downward is considered to be positive. Similarly, to the section, left hand side clockwise movement is considered as positive. Right hand side anti-clockwise or counterclockwise direction is considered as positive. And when you have to use the equilibrium condition, and then you can assume to the right side, you can assume this as positive initially. If you are getting a final answer negative, then the sign will change. But initially, you can assume this way. Mostly, we will not be using this. In short, it is just equilibrium. If you understand what is equilibrium, then very easily you can calculate the shear force and bending moment. Please remember these two sign conventions in order to easily find out shear force and bending moment. And last part of this video, we are going to get a relation between load, shear and bending moment. It's going to be very helpful when we draw the shear force bending moment diagrams. So we take a distributed load case on a simply supported beam, and you take a small length delta x that is magnified here, and I have made the assumption as we have made, right, for the equilibrium. Okay, so the left section or C, at C, the shear force, the internal force is V and moment is M, clockwise upward. And at C dash, there's small incremental increase in shear force at C dash. Similarly, bending moment also. The external force W, we are changing into point load, which will be passing through the centroid. Here the assumption is rectangle, though there is small change in this. Okay, and we are assuming that to be rectangle, so it is passing through exactly half of delta x. Okay, so W delta x is the shear force, and which is centrally acting, and these are the external forces. Now I am going to use the equilibrium condition. So upward is positive, summation of Fy equal to 0, V is positive, and V plus delta V is negative, and W delta X is also towards down, so negative, equal to 0. It is nothing but an equilibrium equation. So delta V equal to minus W delta X. So if delta X tends to 0, and we get dV by dx equal to minus W. This W we call it rate of loading or simply load. Okay, and V is the shear force. So based on on seeing the distributed load, we are able to get the slope in the shear force diagram. we have a load diagram and shear force diagram and bending moment diagram. So based on these relations, we will be obtaining the load diagram, shear force diagram and bending moment diagram. And now we take the moment about C dash equal to 0, right? M plus delta M is acting here in this section. Counterclockwise is considered to be positive and minus M. Then V into delta X. This V will produce a moment. This V will not produce a moment. But this upward V will produce a clockwise moment. That is why it is negative. Then W delta X force will produce an anti-clockwise moment. The perpendicular distance is delta X by 2, half of delta X equal to 0. And the second term is very small and we can ignore it, neglect it. And if you consider only this portion of the equation, we get dm by dx. So these two relations are very, very important. From the shear force diagram, we'll get the slope of the bending moment diagram. Okay. Further, we can extend this and get the integration between any two sections. Say, for example, between C and D, we can integrate and find out shear force. I'm not going to use strictly the graphical method, or I'm not going to use the integration method. I'm going to use normal function method to find out the shear force and bending moment. Uh, in this course, we are not graphically perfectly with scales. We are not going to draw the shear force bending moment diagrams. We are going to understand how the variation of shear force and bending moment throughout the length of the beam. For that, we will be drawing shear force bending moment diagrams, roughly, not to the scale. Okay, we will discuss those in our next video, in which we will start with cantilever beam carrying point load, point loads, then UDL loads, then combination of UDL and point loads, how to draw shear force and bending moment diagrams, how to determine the shear force bending moment at different sections. We will be discussing in our next video. Thank you.